about the most important repeated questions from RCC. First question. The maximum strain in concrete at the outermost compression fiber in the limit state method of design of a flexural member according to IS 456 is option A 10020, option B 10035, option C 10055, and the last option D 10015. So first of all, for answering these type of questions, we have to know the concepts of concrete design. The curve is a combination of parabola and rectangle. Strength of concrete in a structural member will be 33% less than the cube strength due to the size and slenderness effect. So we assume only 67%, 0.67 FCK. Why you are assuming 67%? The actual strength in the site that you are getting will be 33% less than the concrete cube strength due to the size and slenderness effect. So we are assuming that 67%, 0.67 FCK. Now, for the design purpose of structure, design strength is 0.67 FCK divided by factor of safety, which is 1.5. So 0.67 FCK divided by 1.5, which is equal to 0.45 FCK. So the design strength will be equal to 0.45 FCK. This is the design curve. Here you can see three curves. First, characteristic curve. This is the assumed compressive strength of concrete FCK. Then we are assuming that this actual characteristic strength will not be getting in the site due to the size and slenderness effect. So this actual characteristic strength that we are getting in the cube strength test will not be getting, only 67% of that strength actual getting. So it is 0.67 FCK. Now for designing purpose, we are taking a factor of safety 1.5 also here. So 0.67 FCK divided by 1.5, that's 0.45 FCK. Now here from this graph, we are understanding that the maximum strain in concrete under compression is 0.002. And maximum strain in concrete under flexure is 0.0035. Maximum shrinkage strain in concrete is equal to 0.0003. And maximum stress in concrete is equal to 0.447 FCK, that is almost equal to 0.45 FCK. Maximum stress divided by design stress in steel is equal to 0.87 FY. Maximum design stress in steel is equal to 0.87 FY. This is the stress strain curve for limit state method of design. And here the curve is parabolic up to 0.02% of strain, then linear up to failure. So here our answer is option B, 0.0035. The maximum strain in concrete at the outermost compression fiber, the limit state method of design of a flexural member according to IS 456 is 0.0035. Strain at failure for mild steel is equal to Fy divided by 1.15 ES or 0.87 Fy by ES. And strain at failure for HYSD is greater than or equal to 0.002 plus Fy divided by 1.15 ES, or it is equal to 0.002 plus 0.87 Fy by ES. Once again, I am telling here that topmost curve is a combination of parabola and rectangular. It's a characteristic curve for cube. And then we are assuming that due to size and slenderness effect, the overall strength is reduced 33%. So it is 0.67 FCK for structure. This second one is for structure. Then the third curve is design curve. For making the structure stable, we have to consider a factor of safety of 1.5. So 0.67 FCK divided by 1.5, which is equal to 0.447 FCK, almost equal to 0.45 FCK. Okay, these are all about characteristic curve for concrete. Stress strain curve is rectangle and parabola. And then you can move to the next question. in a singly reinforced concrete beam, if the stress in concrete reaches its design strength later than the stress in steel reaches its design strength, then the beam is said to be option A over reinforced, option B balanced, option C critically balanced, option D under reinforced. For answering this question, we have to know balanced section, under reinforced section, and over reinforced section. Here it is clearly mentioned that the stress in concrete reaches its design strength later than the stress in steel reaches. So it means the stress in steel reaches earlier than the stress in concrete. So it is under reinforced section. So here, before failing the structure, the steel reaches its design strength maximum. So we will get time to escape. If it is over reinforced, the stress in concrete reaches its design strength earlier than the stress in steel. So in over reinforced section, sudden failure occurs because stress in concrete reaches earlier than the stress in steel. So here the answer is option D, under reinforced. You can check the other options. Over reinforced. What is an over reinforced section? For an over reinforced section, the actual neutral axis will be greater than critical neutral axis. For a balanced section, actual neutral axis will be equal to critical neutral axis. And for an under reinforced section, actual neutral axis will be less than critical neutral axis. So these are all about over reinforced, balanced, and under reinforced section. Which section is the best for construction? Under reinforced section, because if you are using under reinforced section, we will get time to escape, and there will be a time lagging between the collapse of building, because the stress in steel reaches its design strength maximum at the earliest. After that only concrete reaches its design strength. So under reinforced section is adopted for all building constructions. We are not preferring over reinforced section because here the concrete reaches its design strength earlier than the steel, and it is not preferred for structures. So option D is the answer. Let's move to the next question. Recommendation for an international code of practice for reinforced concrete published by European Committee for Concrete in 1963 is generally known as option A, Red Book, option B, IS 456, option C, Blue Book, and option D, ACI 380. Here the answer is option C, Blue Book. Blue Book is a book published by European Committee for Concrete in 1963, and it is a recommendation for an international code of practice for reinforced concrete. Option C is the answer. Recommendation for an international code of practice for reinforced concrete published by European Committee for Concrete in 1963 is generally known as Blue Book. Next question. Compaction factor test is carried out on concrete to determine option A, compressive strength, option B, tensile strength, option C, workability, and option D, setting time. And we know that compaction factor test is carried out on concrete to determine workability. So option C is the answer. And let's check the other options. Compressive strength. How can we determine the compressive strength of concrete? We can determine it by Q test. How can we determine the tensile strength of concrete? The tensile strength of concrete estimated to be less than 10% of its compressive strength. The low tensile strength of concrete explains the using of reinforcement bar in areas of tensile stress. And the split cylinder test used to estimate the tensile strength of concrete. See here a cylinder concrete specimen of 150 mm diameter and 300 mm length are placed in the apparatus, and a compressive load is applied uniformly until the concrete split. A metal strip is placed above the concrete specimen to ensure a uniform distribution of the compressive load to the concrete sample. The compressive load at the time of splitting is measured and recorded. Tensile strength of concrete can be calculated using the formula UP divided by pi dl, where P is the compressive load at the failure, D is the diameter of the specimen, L is the length of the specimen.
Here, workability. Workability is the amount of work to produce full compaction. The compaction factor test is carried out on concrete to determine workability. In the compaction factor test, the degree of workability of concrete is measured in terms of internal energy required to compact the concrete thoroughly. A compaction factor of 0.95 represents flowing concrete having high workability. 0.92 represents plastic concrete having medium workability. 0.85 represents stiff plastic concrete having low workability, and a compaction factor of 0.75 represents stiff concrete having very low workability. The compaction factor test is designed primarily to use in the lab, but it can also be used in the field. The degree of compaction, called the compaction factor, is measured by the density ratio, that is, the ratio of the density actually achieved in the test to density of same concrete fully compact. Now, the next option is setting time. We know that setting time of concrete can be measured using normal consistency test, that is, Bicat apparatus test. The initial setting time of concrete should not be less than 30 minutes, and the final setting time of concrete should not be less than 10 hours. Let us move to the next question. In a reinforced concrete beam not subjected to torsion, side-face reinforcement is required if its overall depth is more than option A 750 mm, option B 450 mm, option C 300 mm, and option D 500 mm. In a reinforced concrete beam not subjected to torsion, side-face reinforcement required is 750 mm. Option A is the answer. In a reinforced concrete beam not subjected to torsion, side-face reinforcement is required if its overall depth is more than 750 mm. So, option A is the answer. Sixth question. In a reinforcement concrete, retaining wall shear is provided if option A, shear stress in the vertical stem is more than excessive. Option B, shear force in the toe slab is more than that in the heel slab. Option C, retaining wall is not safe against sliding. Option D, retaining wall is not safe against overturning. For answering this question, we have to know the major forces acting upon a retaining wall. So here, shear key is provided in the retaining wall to stop sliding. If the retaining wall is not safe against sliding, shear key is provided. So option C is the answer here. Let's discuss the major forces acting upon a retaining wall. So the major and various types of loads and forces acting on the retaining wall are lateral earth pressure, surcharge loads, axial loads, wind on projecting stem, impact forces, seismic earth pressure, seismic wall, self-weight forces, etc.
Seventh question. The total compressive force at the time of failure of concrete beam section of breadth B without considering the partial safety factor of the material is option A 0.36 FCK XUB, option B 0.54 FCK XUB, option C 0.87 FCK XUB, and option D 0.67 FCK XUB. For answering this type of questions, we have to know to draw the stress diagram of concrete. Here, the total compressive force at the time of failure of concrete beam section is asked. If we are considering a beam section, the upper portion is compression zone and the lower portion is tension zone. So, if you are considering neutral axis, above the neutral axis considered as compression zone, and below the neutral axis is considered as tension zone. Here, they are asking total compressive force at the time of failure of concrete beam section. So, we are considering the upper portion up to neutral axis here. Let the depth of the beam be small d and breadth be b, small b. We have to draw the stress diagram of concrete. We know that the characteristic compressive strength, cube strength, not cube strength, the characteristic compressive strength of a structure will be 0.67 FCK. If the cube strength is FCK, then the structural strength will be 0.67 FCK because 33% reduction will be occurring due to slenderness effect and size effect of the structure. So here we will consider the top as 0.67 FCK. Then we will draw like this. In this diagram will be the upper portion as rectangular and the lower portion as parabolic. So here it will come as 3/7 XU, then 4/7 XU here. And the bottom is tension zone 0.87 FYAST here. So how can we calculate from this stress diagram total compressive force? Total compressive force is equal to area of stress block whole into width. So what is the area of stress block here? Topmost question here 0.67 FCK into 3/7 XU whole into B. The area will be 0.67 FCK into 3/7 XU whole into width of the section. That is the total compressive force in that area. So 0.67 FCK into 3/7 XU whole into B. Plus, what about this section? Here it will come as 0.67 FCK into 4/7 XU whole into 2/3 because this parabolic nature here. So we will multiply by 2/3 whole into width of that section will give total compressive force in that section. So whole into B. So it will come as 0.29 FCK XU plus 0.25 FCK XU whole into B, which is equal to 0.54 FCK BXU. So our answer is option B, 0.54 FCK BXU. So total compressive force at the time of failure of a concrete beam section of width B without considering the partial safety factor of the material is 0.54 FCK BXU. So our answer is option B, 0.54 FCK BXU. Eighth question. The characteristic strength of concrete is defined as that compressive strength below which not more than option A 10% of results fall, option B 5% of results fall, option C 2% of results fall, and option D none of these. We know that the characteristic strength of a concrete is defined as that compressive strength below which not more than 5% of test results fall. So option B is the answer. Ninth question. The modulus of rupture of concrete gives option A the direct tensile strength of concrete, option B the direct compressive strength of concrete, option C the tensile strength of concrete under bending, option D the characteristic compressive strength of concrete. And the answer is the tensile strength of concrete under bending. The modulus of rupture of concrete gives the tensile strength of concrete under bending. Option C is the answer. Let's move to the next question. Which one of the following set of values give the minimum clear cover for the main reinforcement in the slab, beam, column and footing respectively according to IS 456/1978? Option A 20, 25, 30, 37. Option B 5, 15, 25, 50. Option C 15, 25, 40, 75. And option D none of this. Here the question is asking about the clear cover length of different structures, that is for slabs, beams, columns and footings. Here we know that for slabs as per IS code we are using a minimum cover of 15 centimeter. So 15 to 20 centimeter covering length is given for the slabs. So it is 15. And for beams the covering length, that is the 25 centimeter cover block is used. 25 to 30 is the range of covering length for the beams. And for columns, we are using 40 centimeter, not 40 centimeter, 40 mm cover block. For slabs, we are using 15 mm cover block. That is 15 to 20 mm covering length are used for slabs. And for beams, we are using 25 to 30 mm covering block. That is 25 mm covering length is required for the beam minimum. And for the column, 40 mm minimum covering length is required. And for footings, it is 75 mm covering length. Where the contact with soil is coming, we are giving 75 mm covering block. So our answer is option C. For slabs, option C. For slabs, the covering length is 15. For beams, 25. For columns, 40. And for footings, 75. Option C is the answer. Let's move to the next question. The hydration of cement takes place in the presence of water during concrete setting over a period of option A 21 days, option B 14 days, option C 28 days, and option D 7 days. And we know that the hydration of cement takes place in the presence of water during concrete setting over a period of 28 days. Option C is the answer. 12th question. The permissible bending stress in concrete for M20 grade is option A 3 Newton per mm square, option B 4 Newton per mm square, option C 5 Newton per mm square, and option D 7 Newton per mm square. The answer is option D 7 Newton per mm square. The permissible bending stress in concrete for M20 grade is 7 Newton per mm square, and the permissible bending stress in concrete for M15 grade of concrete is 5 Newton per mm square, and the permissible bending stress in concrete for M25 grade concrete is 8.5 Newton per mm square. The permissible bending stress in concrete for M30 grade concrete is 10 Newton per mm square. Permissible bending stress in M40 grade of concrete is 13 Newton per mm square. The permissible bending stress in concrete for M45 grade of concrete is 14.5 Newton per mm square. The permissible bending stress in concrete for M50 grade of concrete is 16 Newton per mm square. So here they are asked about M20. So for M20 grade of concrete, the permissible bending stress is 7 Newton per mm square. For M25 it is 8.5 Newton per mm square. So our answer is option D 7 Newton per mm square. Let's move to the next question. The permissible tensile stress in steel for MS bars is option A 140 Newton per mm square, option B 230 Newton per mm square, option C 190 Newton per mm square, and option D 130 Newton per mm square. And the answer is 140 Newton per mm square. The permissible tensile stress in steel for mild steel bars is 140 Newton per mm square. Option A is the answer. Let's move to the next question. In an under-reinforced section of RCC beams, the depth of actual neutral axis is option A equal to the depth of critical neutral axis, option B less than the depth of critical neutral axis, option C more than the depth of critical neutral axis, and option D none of these. And we know that in an under-reinforced section of RCC beam, the depth of actual neutral axis is less than the depth of critical neutral axis. Option B is the answer. In the case of under-reinforced section, XA less than XC means actual neutral axis is less than critical neutral axis. And in the case of a balanced section, XA is equal to XC, that is actual neutral axis is equal to critical neutral axis. And in the case of over-reinforced section, XA greater than XC, that is actual neutral axis is greater than critical neutral axis. Also, we have studied that in under-reinforced section, the maximum permissible stress in steel reaches earlier than the maximum permissible stress in concrete. So, for a structure to be safe, it should be constructed under-reinforced sections. It should be constructed with as under-reinforced section. Now let us move to the next question. In the relation moment of resistance, MR is equal to QBD square for the beam design. The letter Q represents the option A lever arm factor, option B moment of resistance factor, option C modification factor, and option D neutral axis factor. And the answer is option B moment of resistance factor. In the relation MR is equal to QBD square for the beam design, the letter Q represents moment of resistance factor. Here, the moment of resistance of the concrete section is the moment of couple formed by the total tensile force T in the steel acting at the center of gravity of reinforcement and the total compressive force C in the concrete acting at the center of gravity of the compressive strain diagram. The moment of resistance is denoted by M. The distance between the resultant compressive force and tensile force is called lever arm and it is denoted by Z. The intensity of compressive stress varies from maximum at the top to zero at the neutral axis. Therefore, center of gravity of the compressive force is at a distance x by 3 from the top edge of the section. We have lever arm Z is equal to D minus x by 3. Moment of resistance is given by MR is equal to C into Z, which is equal to Bx into sigma CBC by 2 whole into D minus x by 3. Or moment of resistance is equal to P into Z. P. Here P is equal to AST into sigma ST. P into Z means AST into sigma ST whole into D minus x by 3. For a balanced section, the formula is moment of resistance MR is equal to BXC sigma CBC whole into D minus XC by 3, which is equal to AST into sigma ST whole into D minus XC by 3. For under reinforced section, the formula is moment of resistance is equal to T into Z, which is equal to AST into sigma ST whole into D minus x by 3. For over reinforced section, moment of resistance MR is equal to C into Z, which is equal to Vx into sigma CBC divided by 2 whole into D minus x by 2. So here our answer is Q is moment of resistance factor. The relation MR is equal to QBD square for the beam design. The letter Q represents the moment of resistance factor.
If you felt the video useful and informative, please press the like button, share the video and subscribe the channel.